the quantum mechanical model. So, the quantum mechanical model determines the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. So, if we look here, we see the nucleus here in the center, then we see these 1s, 2s, 2p, and 3s orbitals, and we'll talk about this a lot more later in this unit. So it also talks about summary of principal energy levels, sublevels, and orbitals. Once again, we'll get to this more a little bit later on. One thing I do want to talk about, though, it says principal energy level. This is also equal to the period number on the periodic table. So, if you have n equals 1, your element is in the first period. N equals 2, second period, and so forth. Now, if you want to find the maximum number of electrons, in a principal energy level, you need to use the following equation. 2n squared. So if I wanted to calculate the maximum number of electrons in the first principal energy level, I'd have 2 times 1 squared. So 1 squared is 2, 2 times 1 is 2. If n equals 2, I'd have 2 in here. So 2 squared is 4. 4 times 2 is 8. 3. So we'd have 3 squared is 9. 9 times 2 is 18. And then if we had 4, n equals 4, we would have 4 squared, 16. 16 times 2 is 32. Okay. Now moving on, talking about quantum numbers. Quantum numbers are basically the electron's address. So the principal quantum number, symbolized by the lowercase letter n, is equal to 1, 2, 3, 4, ... It could be anything but 0. The next number, the angular momentum quantum number, symbolized by the lowercase letter l, is also called the azimuthal quantum number, and it takes the form 0, ... n minus 1. So for example, we'll do a bigger example in a minute. N equals 3, L would be 0, 1, and 2. I'll explain what that means in a minute. For our L value, our angular momentum quantum number, in an S is equal to 0, P is equal to 1, D is equal to 2, and F is equal to 3. Now our magnetic quantum number, ML, takes the form negative L, 0, positive L. And our magnetic spin quantum number, symbolized by MS, is always equal to positive 1/2 and negative 1/2. So to do a quick example here, say I wanted to figure out my quantum numbers for n equals 3. Now, my L value, remember, it takes the place 0, ... n minus 1. So I always like to put my 0 and then my n minus 1. And my n minus 1 in this case is the number 2, because 3 minus 1 is 2. Now, we only use whole number integers here. So what's in between 0 and 2? The number 1. And since it's a 0, it's an s orbital, this is a p orbital, and this is a d orbital. Now, ML. Since we have 3 sets of L values, we're going to have 3 sets of ML values. So ML, for the first one, since it's 0, it's just 0. Second one, now the one thing with this, you need to repeat your quantum numbers. So we have 0. Since it's 1, negative 1, 0, positive 1. And then the third quantum number, we have 2. So we have to repeat these ones, and we'll learn, and you'll see with the repeating of these numbers once we start doing electron configurations and how this ties in. So now we have 2, so we have negative 2, negative 1, 0, positive 1, and positive 2. And always our MS value is always negative 1/2 and negative 1/2 and positive 1/2. And this is our spin up and spin down, clockwise, counterclockwise. And then the last thing today, we're going to talk about the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle states that it is impossible to know exactly both the velocity and position of a particle at the same time. So we see in the picture here, we see a proton and a moving electron going from left to right. So before the collision, a photon strikes an electron during an attempt to observe the electron's position. Now, after the collision, we see the photon wavelength changes and the electron velocity changes. The impact changes the electron's velocity, making it uncertain. That's why it's impossible to know the velocity and position of a particle at the same time. And this concludes our video on the quantum mechanical model, quantum numbers, and the Heisenberg uncertainty principle.